Okay, so let's continue with this special topics lecture on spherical geometry, stereographic projection, and hyperbolic geometry. That's where we are today. We're looking at hyperbolic geometry. We're going to try to understand the geometry of a space, a two-dimensional space with Gaussian curvature of -1. We tried to make a surface like that in R3. We made the pseudosphere. It's not complete. It has an edge. So we're going to take another approach. Okay, we're going to take the approach of Poincare, okay, who just invented a model based on what we've just done with the stereographic projection. He says, here's what you got with stereographic projection off a sphere. Let me just jigger it around a little bit and make the conformal factor have some minus signs in it. Okay? He noticed that if you do that, then here's the metric written in complex variable form. And it's easy to check with that switch that k is -1. Okay, so there you have it. There you have a model, okay, of hyperbolic geometry. We want to understand it. Okay. Okay, it's clear that the range of U and V, we're going to be inside a disk of radius 1. Okay, put this metric inside the unit complex disk. That's the Poincare disk model of hyperbolic geometry. Okay, it's also going to be convenient to display the same geometry but in the upper half plane. So in this particular lecture, I'm just going to grab lots of information from your introductory course in complex variables. So I'll be stealing lots of stuff about analytic functions. I'll be stealing a lot of stuff about linear fractional transformations, sometimes called Möbius transformations. Okay. If you need to review it, please do so. I like the book by Alfors. More modern books, I think there's a bunch by Churchill that are popular. They all have this material in it. There's nothing special. I'm just going to use the complex variables so that I can talk conceptually about the problem and not be hung up in a lot of arithmetic. I don't want to reinvent the wheel. Well, I know from complex variables that I can map the disk to the upper half plane, and how do I do that? I'll call the upper half plane the variables h, the complex point in the upper half plane, in terms of a real part j and an imaginary part l. And here's the mapping, okay? And here's the mapping. I put in a point in my Poincare disk, z, and then it maps into the upper half plane like that. Okay. I can motivate that by solving for z and doing the inverse. Okay. So for example, note in this map that the boundary of the disk maps onto the real line. Okay. If I take a point of magnitude 1, that maps onto the real line. Okay, and I can see that. I can see that here. If h is on the real line, okay, then for any point, the distance on the real line is the same for minus I and plus I, and so the magnitude of z is 1. As h ranges from minus infinity to plus infinity, the phase of z ranges from 0 to 2 pi. I can just verify that, and I see that h equals plus I maps onto z is equal to 0. You see that? If h is equal to I, then I map onto z equals 0, so that the middle of the disk, okay, maps to the upper half plane, just the point up the imaginary axis by 1 unit. That's enough for me to know that the interior of the disk maps into the upper half plane. None of the points goes to the lower half plane. And again, it's a linear fractional transformation. If I know how one point maps from the interior to the other space, then I know everything that there is, and I'm done. I don't have to check it point by point because I'm relying on all the stuff I know about linear fractional transformations. So the disk, okay, is then mapped by this transformation into the upper half plane, okay, and I can compute for any particular situation, and it's important for me to notice, okay, that as h ranges along the real axis, okay, that I'm mapping onto the disk, the edge of the disk, and z ranges from 0 to 2 pi, okay. Okay, so that's the geometry of the map. Okay, so the edge of the upper half plane, the real axis, maps onto the edge of the disk, the points with radius 1. Okay, I can find the induced metric on the upper half plane. I just need to take dz prime, and zz prime, and write them in terms of h, which is j plus il, and that's an easy exercise, and I do it here. Okay, well here's the relationship. So I can compute dz by dh. Okay, I can compute 1 minus zz bar. These are the ingredients in the metric. Okay, so do that. Okay, take the product of dz with dz bar. It's just the arithmetic to be done, and it's all collected in okay, in the supplementary lecture on hyperbolic geometry. Okay, and so what you'll find then when you complete it is a rather elegant thing, that the metric in the Poincare disk becomes this metric in the upper half plane. Okay, both of them are conformal to a plane, and the weighting in the upper half plane is by 1 over L squared. Okay, so the metric gets smaller and smaller the further you get away from the real axis. I can check easily that k is equal to -1 for this metric. This is a very handy little metric for checking that. For example, here. Yeah, I read off that E is 1 upon L squared, F is 0, G is 1 upon L squared. Put that into Gauss's excellent theorem, and quick as an eyelash you get -1. So that's a nice parameterization to see the curvature of it, right? Okay, so there I'm just sitting with my ordinary complex spaces, the disk and the upper half plane. To me, I'm looking at them, they're flat, right? But they're not flat if you look at them through these metrics, right? Through these metrics, you have models of hyperbolic geometry. So I can refer to either the Euclidean distances in those spaces. Okay, that's just the du squared plus dv squared. Okay, or the j squared plus dl squared. Or I can talk about hyperbolic distances, and that incorporates these denominators in the actual metric of interest. Okay. 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 Now we're doing the geometries of the disk model or the upper half plane model, and we have to learn how to move figures preserving the shapes and sizes. So we need the symmetries and isometries of each model. Right, when I do the Euclidean geometry of objects in R3, I think about the symmetries. I take an object and I want to compare it to another object, so I move them and make them coincident, see if they're the same size, that they have the same angles, and what all. So I have to know how to make those movements. When I move these objects, translation or rotation in R3, I know that those are isometries, that they don't change the relative distance using Euclidean metric between the points of those objects. I need the similar considerations in these spaces, and this metric is not familiar to me, so I'm going to have some interesting surprises here. So I'll consider the upper half plane model. In that case, then I know my metric is dh bar divided by the imaginary part of h quantity squared. Right, the metric was proportional to the 1 over the distance squared to the real axis. That's the imaginary part of the complex variable h. So so I can look at some symmetries. Translations at constant L imaginary part of H, that leaves things invariant, so I can move objects, okay, as long, along lines of constant imaginary part. Okay, I can make dilations for through a number which is real and positive. Well, that's a new one, right? I can scale. I can scale my objects, and if I do so, it leaves the metric unchanged. Okay, and that's just looking at the dimensional analysis here. I have H bar upstairs, and I have H squared downstairs. So if I do a scaling for a real one, okay, for a real parameter A, it doesn't change anything. So dilations are actually a curious symmetry in this funny space. And you think that's odd. Okay, here's the kicker. Inversions. I can turn the things inside out, okay, pull them apart, and that's a symmetry of this space. H going to minus 1 over H is a symmetry. Why the minus? Well, it has to be an operation that leaves me in the upper half plane. Okay, I need that minus so that the imaginary part of the image of H is also in the upper half plane, and so because H is in the denominator, I need a minus sign to get me back to the upper half plane. So let's take P as being minus 1 over H, and just ask if that leaves a metric invariant. Okay, well, P is 1 over H, so dP is dH over H squared, etc., etc., etc. I just do my little complex analysis exercises. I don't want to dwell on it here because it's something you just sit down and do. It's more fun for you to verify it yourself. And you will verify that dH bar over imaginary part of H quantity d squared, that's the metric in the upper half plane, is dP bar over imaginary part of P quantity squared. It's unchanged. Okay, so isn't that's really curious. Okay, that's a symmetry of this system. Lesson: these three symmetries can be applied sequentially to produce a linear fractional transformation, a Möbius transformation of the form H goes to AH plus B over CH plus D, where A, B, C, and D are real and have a positive determinant. Just putting these three things together, okay, I can make a linear fractional transformation of a restricted kind, but I have to keep the upper half plane has to map into itself, and so there are restrictions on the parameters, more restrictions than a typical linear fractional transformation. But this one does what I want to do. Okay, so hopefully you have the experience in the elementary theorems of complex analysis to know that if these things are the case, you can just construct a sequence of them, okay, to make a linear fractional transformation. I think you can show that for yourself, but it's just relying on constructions in complex variables that are relatively well known. You know, I'm sure you've solved lots of problems in potentials theory by mapping them onto a theory of complex variables in 2 dimensions, and then using linear fractional transformations to push the boundaries around to match the boundaries of your given electrostatics problem, for example. So hopefully you've done some of that, and if not, you can just take the supplementary lecture and fill in the steps here. I do a little bit of it, but not everything. We recall that Möbius transformations preserve angles between intersecting curves. Okay, that's true about linear fractional transformations. Okay, and in general, linear fractional transformations map lines and circles to lines and circles. Okay, and avoiding the singularities. They're analytic functions, and analytic functions preserve angles between intersecting curves. Okay, so if G is a mapping of this form, it takes the imaginary axis IK to another line, which is perpendicular to the real axis, or to a circle, which is perpendicular to the real axis. So G maps the real axis onto itself, and if I put in other lines like a vertical, it can map it can map the vertical line by linear fractional transformation to another vertical line. If it has to remain vertical, right? Because if I have a mapping of this linear fractional transformation form, it preserves angles. So the angle between this axis and this axis has to be preserved. Now it can map, in addition, it can map lines into circles. But when it does so, it has to preserve angles. So if it takes a line, a straight line, which is perpendicular to the real axis, it has to make a circle which is also perpendicular to the real axis. Okay, this is very important when I come to looking for geodesics. In fact, now let's talk about that. Let's find the geodesics. Well, there's one geodesic that's obvious. A vertical line is clearly a geodesic. If I'm just going to look at 2 points which have the same real part but different imaginary parts, then the distance is dk over k. That's just the metric. In this particular case, I'm writing hyperbolic distance between a point ik1 and ik2. Okay, so they're just on the imaginary axis. Okay, their distance is given by dk over k. It's the logarithm of the ratio. Okay, now I'm sure that the straight line is the geodesic between those two points, because the metric goes like 1 over the imaginary part of h quantity squared, and a straight vertical line minimizes it. But if this is the weighting 1 over the imaginary part of h, so I want to go straight up between 2 points having the same real parts, but just differ in their imaginary part. To get me the shortest hyperbolic distance. If I put a wiggle in that curve, okay, then it's clear that I'm going to get a larger contribution from the additional dk in the wiggle than if I go straight up. Okay, so I can suppose, for example, that G maps 2 points onto a circle. Okay, so I can easily calculate the distance between the 2 points if they're separated only by the imaginary parts. But then I can imagine making a map of those points through a linear fractional transformation to 2 other points, which might in fact lie on a circle, and I'm guaranteed, because G is a symmetry, that the distance of the points before and after is the same. So there I've learned something very non-trivial. Okay, so now I can calculate the hyperbolic distance between a point here on the circle and a point here on this circle, and know that distance is geodetic. Okay, and I know how to calculate it through the mapping to just a simple logarithm. So let's find, for example, the geodesic between 2 points h1, which has the real part nu1, okay, plus an imaginary part which is w1, okay, and another point which has a different real part but the same imaginary part. So here's h1 and here's h2. Okay, so I have to draw a geodesic between them. Okay, I know full well already that it's going to be a circle, okay, which is perpendicular to the real axis. So I've drawn the circle there, okay, like that. I know how to draw that circle. Okay, for example, here's a construction that gets me that circle. I draw a straight line between h1 and h2. I bisect, I drop a perpendicular. That gives me the center of the circle. Okay, and then the Euclidean distance to h1 is the same as the Euclidean distance to h2. Okay, I get out my compass and I draw this semicircle. I'm guaranteed, okay, that this angle is 90 degrees, that this angle is 90 degrees, so that circle is indeed a geodesic. That's a geodesic. So I can calculate then the distance between h1 and h2. Okay, mapping back to the imaginary axis like that. Okay. Okay. Now make a mapping to a vertical geodesic. Here's the way to do that. G of h will get me back to a vertical geodesic. I can note here that G of I have the J1 and the J2 in this picture. Okay. J1 over here, okay, on the real axis, and J2 over here on the real axis. I note that G of J2 is equal to 0, that G of J1 is infinity. Okay, so the image of the circle is a vertical straight line. It's a vertical straight line, then I know how to calculate the distance between, between the images, and that gives me the distance between the original 2 points. Okay, and our logarithmic formula applies. So that's pretty slick. Okay. And now it's interesting in this hyperbolic geometry to consider parallel lines. In Euclidean plane, of course, we know that through any point P, not on a line L, there is only one line parallel to L. Okay. Well, we studied this point for the sphere, okay, and we remember that great circles, geodesics, always intersect. They intersect each other twice. Okay, so we won't be too surprised if we find another violation of the Euclidean parallel line postulate. Okay, so parallel line postulate doesn't hold in the case of hyperbolic geometry, because here I can make some pictures. Here I can have a line L1 that goes through on the disk. Okay, that goes to the origin. Okay, I know that another geodesic will be a semicircle that intersects the edge of the disk at 90 degrees, and I can imagine here that these 2 points, that L1 and L2, only intersect one another at infinity. So those 2 lines are parallel. Okay, right? They only intersect at infinity. That's what you say in Euclidean geometry. They don't intersect in a finite space. Okay, but here I can do better than that. Those lines might be called parallel. They only intersect at infinity. I can make ultra-parallel lines. Here are 2 geodesics which never touch. Okay. Okay. So I'm in a 2-dimensional space. Remember. Okay, in a 2-dimensional space in Euclidean geometry, if you give me one line and a point off that line, I can only draw one line that's parallel to the original one. Well, it's clear here. I can draw lots of geodesics which never intersect a given one, L1. Here's an L2. I can make an L2 prime, an L2 triple prime, and so there are things called ultra parallel lines on the hyperbolic disk. Okay, so finally, why don't we just look at the hyperbolic distance in the disk model and compare it to some of the metrics that we've already seen. So I want to calculate the hyperbolic distance from the origin, okay, of the disk model to a point Z, which has a radius R and a phase phi. Okay, so that's a point I write in variables U and V, real and imaginary part, U and V like that. Okay, just writing for Z like that. And here's my metric on the disk model. U and V are restricted between 0 and 1. I can write that in polar coordinates. I'm just making a polar coordinate change of variables, which is appropriate because I want to find the length of a radial geodesic. So the radial geodesic hyperbolic distance, rho from 0 to R, e to the I phi. Okay. Well, clearly the phase doesn't matter, as you see. Okay. And so I'm just moving out in R. Okay. And so I'm looking at this bit of the metric. Okay. I'm doing it just a linear length. Okay, so it becomes 2 dt over 1 minus t squared, just the square root of this stuff. Okay, because this is the length squared. Okay, and that's my hyperbolic distance from 0 to R. It has no phi dependence. You know, I start at the origin. I go in any direction away from the origin along in the Poincare disk, and I get the same answer. The answer is twice inverse hyperbolic tangent of R. inverting that, I see that r is equal to the tangent of rho over 2. So that's my mapping, okay, and and I see that as I approach, right, as I approach the edge of the Poincare disk, that my distance in hyperbolic measure is infinite. Okay. Let's write the metric in terms of rho, right? The disk is its Euclidean size is what it is, but its hyperbolic length is unbounded. It's unbounded. Its hyperbolic distance to the edge is quite infinite. You see that in the denominator of the metric. The denominator going to 0 as r approaches 1, and then that's reflected in the character of the integral here. It's interesting to write the metric in terms of rho, so now I'm going to write the metric in terms of my hyperbolic distance, okay? And so r is tangent of rho over 2, so I can take dr and okay, differentiate it with respect to rho, and here's my arithmetic. I have to take 1 minus r squared, write that in terms of hyperbolic functions. It's cosh to the 4. You check my arithmetic, okay, and I need to know that cosh to the 4 times tangent squared is half sinh of rho. So I have to do a little bit of arithmetic here. It's just hyperbolic function identities, okay. If you're not slick at them, well, look it up in Wikipedia and verify this. It's just plugging away with exponentials and minus exponentials. The point being here, the dr squared is my metric on the Poincare disk, and now rewriting it in terms of hyperbolic variables, rho and phi, I get d rho squared from my exercise, and I get sinh squared of rho d phi squared for the angular arc in my disk. It's easy to verify that k is equal to -1 for this metric, right? Okay. Well, just compare this metric to the metric on the sphere. Okay, it has the same shape. D rho squared, d theta squared for a sphere radius 1. Theta is the geodesic distance. Okay, and then I have for my hyperbolic space sinh squared of rho. Okay, and in my spherical space I have sine squared of the hyperbolic distance theta, and then d phi quantity squared. So the only switch is from a sine to a sinh. Okay, well, that of course sine is critical. It changes k from +1 to -1, as you can easily check, and that's why it's called hyperbolic geometry. We have a very slick form now for the metric, and we can make measurements of distances in this form. Okay, so that's our introduction to hyperbolic geometry. There's lots more games you can play, and take a look at the references in supplementary lecture number 4 for some of those references. They're quite a lot of fun, and you can take a look at geodesic triangles in the hyperbolic disk or the upper half plane. Confirm the Gauss Bonnet Theorem. You can confirm that hyperbolic geodesic triangles have the property of the triangles on the sphere have, that if they have if they're similar, they're actually congruent. Okay, it's hyperbolic, a hyperbolic form of the of geometry rather than the cosine form of geometry that we're used to. So those are interesting things to do. A little bit too particular for these general lectures, but take a look at it and have some fun.